everybody, I'm Elisa and I'm back and we're talking about the circulatory system. The part is the blood. And right now we're continuing talking about the idea of the ABO blood groups and antibodies and antigens and agglutination and all of that clumpy, matchy, mismatchy stuff. Okay, so we talked a little bit about the idea of there being antibodies and agglutination. We talked about in video 10 ABO blood groups, right? And we talked about surface proteins on each one of these, right? And they are different and they cause different immune responses. And one of those immune responses is the clumping in the veins or the blood vessels of mismatch. And so here's kind of like a representative, right? So like these antibodies, these agglutinins, right? They're small and like you can see them like here's their little surface binding protein right here and they're checking each one of these red blood cells as they go by and they say like, "Oh, are you one of mine? Okay, then you're okay. Oh, are you not one of mine? Oh, we're gonna clump on you and we're gonna signal for your destruction," right? So like if these are all like type, oh, the green on green didn't work well. So these are all type A, for example, right? Like this is a type A bloodstream and here's a type A cell. And this is, oh no, here's a type B in here. That's essentially what's happening. Okay. So red blood cell antigens are agglutinogens, right? So they agglutinate, they stick on there. And the ones that begin the process gen uh, do it based on these glycolipids on the red blood cell surface, A's and B's, for example. Antibodies or glutinins, right, are the items that are going to be gluten or are globbing onto them. We find them floating in the plasma, right, because they're small, these little small, like dissolved proteins, essentially. Anti-A will bind always to or antigen A, right, A blood types. And then anti-B will always bind to the B blood types. And so you don't form antibodies against your own antigens because like why would you, right? Like that's you. Like you wouldn't signal that yourself is an invader. And so if that happens, that's as an autoimmune response, and that is like some bad news bears. Okay. That's actually saying like it's very serious condition and it needs to be recognized and treated immediately. It's very bad for an individual's health. And so here's one of the things we use in the lab. Sometimes you can use blood types and actually mix them. But since we kind of just encourage people bloodletting in the lab and then mixing their blood together with other students, this is another way you can do it. You can actually use this like kind of fake blood and kind of fake blood antibodies, and you do this experiment, right? Where you have like, here's like a type A, a type B, and a type AB, and a type O. So you can see for type A and type B that there's always one that doesn't clump, right? So that's one that's like recognizing self, and they're like, this is okay, we're going to stay fluid. But when you have an invading blood type, and it's recognized, you see that it kind of clumps up. And so it's that clotting that the agglutinins are kind of making everything stick together, right? And so that's like the clotting, agglutination phenotype. And so for type AB, these antigens and antibodies are going to be, highly recognized. So everybody's going to get clumps. But if you have like a type O blood, there is just nothing for them to stick to. So everything remains fluid. So this is why we have a universal donor. Because you can take this type O blood and put it to anybody's veins and no one's going to clot. That's great. And then we have this other individual, which is a universal recipient, which you can take any type of blood and put it in, and they're not going to clot because they recognize both, right? So that's a self. So the donor's red blood cells can't agglutinate, or else it's going to form these clots in the bloodstream, and they're going to get degraded, and it's going to be really bad. And so this is what's known as the transfusion reaction. We really don't want to see this happen. So each antibody can attach to several foreign antigens on several different red blood cells at the same time. So it's very complex, the binding. So agglutinated red blood cells are going to block small blood vessels, causing those clots to happen. Also, the blood is going to, the donated blood is going to hemolyze, lysis, right? Think of that. So enzymes are going to come and actually degrade it. And then we're going to start seeing hemoglobin being released over in the matter of hours or days. We'll see yellowing in the blood, jaundice. Eventually, we're going to block out the kidney tubules because it's going to be so heavy, so thick with all of these dissolved parts and broken up parts of red blood cells that we can also um, fall into acute renal failure. So, very specific, very, very immediate renal failure. So here's the effects of a mismatched transfusion, just like a visual, hopefully that's helpful to see. So here's this person is type B blood, right? So there's all these little B blood cells in here. And so then what happened is they got type A donor, right? So back in like the Civil War days, for example, they would just like whoever they take a risk because there was a very low percentage, but still a percentage that somebody would survive. And in the event that a type B recipient received blood from a type A donor, sometimes it would cause these clots, right? And then organs wouldn't get blood. And then also in the bloodstream, they would eventually just become more and more agglutinated and then degraded and then renal failure within a few days. Charles Drew, however, was a really important blood banking pioneer. Um, so Charles Drew was the first Black person to pursue an advanced degree in medicine and was very, very essential in kind of bringing about these ideas that science for a while now has been showing that humans are actually really similar. Like race is a social concept and not even a biological concept, right? And one of the things that he did that was, so he promoted equality, especially during wartime, because sometimes there would be disequal treatment in the hospitals of based on race or based on ethnicity of different patients, right? There wouldn't be enough beds for one ethnicity versus another, and it was tragic and wrong. And so he was a pioneer that helped really kind of show people that this is not how we should move, and this was not scientifically backed. And one of the many important things that Charles Drew brought into the picture was that he used plasma rather than whole blood. So he actually took out the fluid part of blood from all of the red blood cells, and that really caused a lot fewer transfusion reactions. Um, during wartime, which was just absolutely instrumental. And so, I don't know. I think it's just so cool because he has this like poster in the background, right? And if you've ever worked in science, like that is so quintessential science stuff. I love that. All right. So transfusion reactions. Let's talk about what that is. Whenever possible, you should try to match the blood types, but a lot of times you can't. They would find, especially they would call them starting back in the Civil War, these what they'd call the angel donors, right? And it turned out most of these angel donors had type O blood. We find them, they are usually the universal donors, especially if they're rhesus negative. And so, since they don't have antigens of A or B on their red blood cells, they don't cause reactivity when their blood is donated to these individuals, right? Like everything works out pretty well. Depending also on rhesus factor, a few other things. However, it's kind of hard because they specifically have to have type O blood in return, right? So they can't receive type A or type B back. Um, Type AB is, luckily for them, the universal recipient. So they can take anyone's blood. They can take O, they can take A, they can take B, they can take AB because their body recognizes all of the different surface antigens as self, and there are very few of these folks out there. Um, right. So rhesus factor. So rhesus is a subgroup also. So it's just another type of surface antigen. We actually discovered rhesus factors, or these agglutinogens, CDE, in the rhesus monkey. Rhesus D is actually the most reactive. And if a patient is considered to have rhesus positive, if they actually have that D antigen. This is also a signal of our evolutionary heritage. Like a rhesus monkey is not an ape, but a primate. And we're still that closely related that we were able to make this discovery in rhesus monkeys. So we still carry this from like a common ancestor. So that's kind of crazy stuff, right? Evolution does it again. So rhesus factors, rhesus frequencies are going to vary among ethnicities. So an ethnicity is an interesting thing. So an ethnicity is usually it's a social concept as well. Um, Oftentimes people in a certain ethnicity or culture, even if they live in the same city, kind of stay in their same culture, right? So that's just, like all the people who maybe play soccer just marry other people that play soccer or have children with other people that play soccer, and then everybody who plays like baseball, they're like, I'm only looking for baseball players and we are going to have baseball player kids, right? And so these like become kind of genetically isolated in that way, right? And so that's where the variation kind of comes into it. But it's rhesus factor can be within anywhere, any of the groups within humans. It's just the frequency within that group is going to be higher or lower. So anti-D agglutinins are not normally present. So they form in individuals who are rhesus negative, who get exposed to rhesus positive blood, basically. So if you have a mom who's rhesus negative and she has a fetus that is rhesus positive or has a transfusion of rhesus positive blood, and that's like her first pregnancy, she won't have problems with that first pregnancy because it's kind of like, when you get a vaccination and you don't really get sick right away from the vaccine because your immune system is just now finding out about it, right? It's the second time though. So like the second pregnancy is going to be the ones because she was kind of in a way vaccinated against that, RH positive, like that positive rhesus factor. And so she's made those antibodies in that period between the first pregnancy and the second pregnancy, right? And so that's one of the reasons it's important to kind of understand the genetics involved in like the parents and the pregnancy themselves. And so there's prevention because luckily it's the 20th century, and there are medications that you can give to suppress an immune response, so that is helpful. Um, right? So here's just a graphic showing that. So here's like here's the fetus, right? And perhaps father was carrying this rhesus positive allele. And so this allele resulted in the mother kind of being exposed for this rhesus positive. And so now over time, her immune system had created like antibodies, right, to D or to this like rhesus positive. And so if you have a second pregnancy with a rhesus positive child, then the antibodies will actually dimerize, and that would cause an immune response and possibly terminate the pregnancy, causing other problems. So that's why we, kind of look for this testing early on to avoid this hemolytic disease of the newborn, right? Because it is preventable now. So in 2 out of 3 cases of HDN involve like an ABO mismatch as well. So the effects are usually mild. Generally, mom has to be like O, and then the fetus has got an antigen, or I'm sorry, an antigen like so like AB or an AB blood type. So it's a relatively low, but still it's worth looking out for, just something to be aware of. Okay, so before we move into white blood cells, I just wanted to say, so that's it for ABO blood groups. There are more blood groups out there, especially when you get into things like organ transplant. But if you have any other questions,